Okay, ladies and gentlemen, let's go ahead and pick up where we left off. If we take a look at why we're even talking about power series whatsoever, the real payoff comes when we attempt to integrate or differentiate a non-otherwise integrable or non-differentiable function by adjusting it into a power series, which as by its nature being a polynomial is absolutely differentiable or integrable, especially if we combine it with some substitution and multiplication. So if we're going to go ahead and integrate something like this, let's go ahead and attempt to go from 0 to x, t cosine t raised to the fifth dt, and you want to integrate that. That is not really that challenging using a Taylor or Maclaurin series, because what we can really do is let's break this up into something a bit more simple. If I simply wanted to go 0 to x on an indefinite integral for cosine t dt, we would simply use the pattern. And the pattern, of course, for cosine, if we go back and we refer to it, we say that is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial cosine, x to the fourth, minus 1 over 6 factorial x to the sixth. That's our standard form. That would be if it were just a straight up cosine. Of course, since it's cosine t, these would need to be t's. But it doesn't frankly matter because we don't have just cosine t. What we have is we have cosine t to the fifth. Well, that is nothing more than a cosine with a t to the fifth substituted in. So all I'm going to do is everywhere I see t in this standard format, I'm going to replace that with t to the fifth. So I use my standard formatting. But everywhere I see t, I'm going to replace it with t to the fifth, t to the fifth, t to the fifth. So now we have the cosine taken care of, the outer function. We also have the inner function taken care of. The only thing we haven't gotten taken care of is this t right here. So if all of this can be replaced here, if I need t times all of this, the nice thing about this is because of the nature of polynomials, t times all of that stuff can actually be combined as like terms rather than cosine t and a t, which cannot be combined as like terms. So I end up with t minus 1 over 2 factorial t times t to the fifth squared plus 1 over 4 factorial t to the fifth to the fourth times t, etc., etc., etc. So in this case, we had t to the 10th. So now we have t minus t to the 11th over 2 factorial plus, that would be t to the 20th, so it'd be one more, t to the 21st over 4 factorial, and so on and so forth. And at this point, integrating from 0 to x dt is no challenge whatsoever because the integration of t is, of course, 1/2 t squared. The integration here is going to be negative, and we're going to have t to the 12th up top. It's going to be 12 times 2 factorial, plus we're going to get t to the 22nd. We're going to get 22 times 4 factorial, etc., etc., etc. Now, of course, we can't integrate on to infinity found at 0 and x. What we're going to need to do is go ahead and throw our x's in because we have now integrated. The upper bound is x, so we throw x's in. 1/2 x squared minus x to the 12th over whatever, that'd be 24 in this case, plus, and that's going to be, gosh, 6 times 22, 6 times 22, 122, 132, 134, excuse me, t to the 22nd, but it's not t anymore, it's now x, plus dot, 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 minus shoving zeros into everything. But since there's a t in every problem, it's going to be minus 0, so that entire section goes away. We now have a power series that represents the integral from 0 to x of t cosine t to the fifth dt. So what was non-integrable prior to the power series is now totally integrable because we turned it into a polynomial, allowing us to plug it in. If they wanted us to find when x is something specific, we could plug it in at this point. So again, it's another opportunity to integrate things that were otherwise non-integrable. So that's really where the whole payoff of this function is. Normally, as in example they give here in the book in example 6, they say find the integral and examine for the sixth partial sum. Since we can't go to infinity, we would only need to evaluate the sixth partial sum, and we would want to evaluate it at, it said, at x equals 0.8. So we would plug 0.8s in everywhere we see x. And so for the sixth partial sum, we could throw all of this together until we get to the sixth partial sum and add it on. That would be the value of the integral at 0.8 using the sixth partial sum, because instead of integrating some function and using some function we can't do, we have taken and we have used a power series that at least around 0 matches close enough to do the integral. All right, with that, that is the point of the Taylor-Maclaurin.